Hey, welcome back. Today, we're diving into an idea that's, well, it's inspired by some of the simplest creatures on Earth, but it's being used to solve some of our most complex problems. Everything from green energy to medicine. We're talking about particle swarm optimization.
So let me ask you this. What can a flock of birds possibly teach a supercomputer? It sounds like the start of a bad joke, right? But the answer is actually powering some of the most incredible technology we use every single day.
And to really get it, we have to start where the idea came from, nature. Just picture it, a flock of birds that turns in perfect, beautiful unison, or a school of fish that dodges a predator like a single organism, even a colony of ants that somehow finds the absolute shortest path to a food source. This is what's known as the wisdom of swarms.
And here's the really wild part. There's no leader. There's no single bird calling the shots for the whole flock. Nope. Instead, every single individual is just following a couple of very, very simple rules. And out of those tiny local actions, this incredibly complex and intelligent group behavior just emerges. It's kind of magic, really.
So you can imagine, some brilliant computer scientists looked at this beautiful, coordinated dance happening in nature, and they asked a huge question. Could we build a digital swarm to solve our problems? And the answer, it turns out, was a massive yes. It led to this incredibly powerful new kind of algorithm.
And that brings us to the star of the show today, particle swarm optimization, or just PSO. Now, I know this definition looks a little heavy, a bit academic, so let's just break it down. Imagine you're trying to find the highest peak in a huge mountain range, but the whole thing is covered in thick fog. Instead of one lone hiker trying to find it, what if you sent out a whole team of hikers? These are your particles. Each one explores a different path, but here's the key. They talk to each other, they share what they find, and together they find that peak way, way faster than any single hiker ever could. That's pretty much what PSO is doing.
So, how does this digital swarm actually work together? Well, it all boils down to two brilliantly simple rules. First, each particle, or hiker, remembers its own personal best. Like a bird remembering the biggest patch of berries it has ever found. And second, it also knows the best spot found by anyone in the entire swarm. Now, it's not a leader in the sense of a boss giving orders. Think of it more like a bright beacon showing where the best solution so far is. And by balancing its own memory with the group's best discovery, the whole swarm just zeroes in on the best possible solution. It's so efficient.
Okay, so we have simple rules, we have digital particles, but what does this actually do? I mean, what's the point? Well, this is where it gets really incredible. Let's take a look at how this algorithm, inspired by a flock of birds, is tackling some huge, real-world challenges.
First up, let's talk about renewable energy. Getting the most power you possibly can from a solar panel is a huge challenge. The sun's angle is always changing, clouds are rolling by, the temperature goes up and down. The best setting for the system is basically a moving target. To solve this, engineers use these algorithms for something called maximum power point tracking. They're constantly hunting for that power sweet spot. And this is actually a really competitive field. You've got different nature-inspired algorithms like PSO, and even one called the cuckoo search algorithm, all being tested against each other to see which is best. And PSO is a major player here, with its digital swarm making sure our solar panels are wringing every last possible watt of clean energy out of the sun.
All right, now for something totally different. Let's see how that exact same logic of finding an optimal moving target can go from producing energy to literally saving lives. We're talking about making cancer detection models way more accurate.
You see, modern diagnostic models, the AIs that help doctors, are unbelievably complex. PSO basically acts like a master tuner for these systems. It, of course, optimizes for accuracy, but it also helps with something called feature selection. That just means it helps the AI figure out which bits of patient data are the really important clues and which bits are just noise. It also handles hyperparameter tuning, which you can think of that like perfectly adjusting all the little knobs and dials inside a high-performance engine to get it running just right. And get this, researchers are even making hybrids, combining PSO with other methods, like spider monkey optimization, to get the best of both worlds, pushing accuracy even higher and giving doctors more reliable tools.
For our third example, let's jump into the world of high-tech robotics. One of the absolute hardest things to do in engineering is to control a system that is, by its very nature, unstable.
And folks, it does not get much more unstable than a triple inverted pendulum. I want you to imagine balancing a long broomstick on the tip of your finger. Now imagine stacking 2 more broomsticks on top of that one. It's an incredibly difficult, almost impossible control problem for a human. But as you can see here, this is where PSO just shines. It takes on that instability and those complex dynamics by automatically tuning the robot's controller. And the result? It figures out the absolute optimal way to keep it balanced, and it does it using the bare minimum amount of energy or torque needed. The algorithm literally teaches the robot how to do this impossible-looking task.
So it's pretty clear that PSO is already this amazing tool that's changing the game in major industries. But you know how it is. Researchers are never satisfied. The hunt for even smarter, even more efficient ways to solve problems is always pushing forward. The future, really, is all about making these digital swarms even more intelligent. We're seeing more of those powerful hybrid algorithms that get the best of both worlds. People are working on scalability so that these swarms can tackle enormous problems with tons of different goals. And they're even figuring out ways to build an expert human knowledge to help the swarm get to the right answer even faster. This whole field of what they call metaheuristics, these problem-solving strategies inspired by nature, it's just exploding right now.
And that really brings us to the final thought here. We started with something so simple, right? An observation about a flock of birds. We saw how that one idea, boiled down to just 2 simple rules, creates this kind of intelligence that can optimize our energy grid, it can make medical diagnosis sharper, and it can master robotics. So the question I want to leave you with is this. If this is what simple swarm rules can do for us today, what are the seemingly unsolvable problems they're going to conquer for us tomorrow?